Hello everyone. Today we will solve few more problems on losses of prestress. So today's first problem. In a post-tensioned beam of length 12 meter, a cable is laid symmetrically with its central 6 meter length horizontal and two straight end portions and sloping at an angle with the horizontal where tangent is equal to 0.075. The cable is tensioned by jacking at one end and is anchored at the remote end of the beam. At the jacking end, the measured stress is 1040 Newton per mm square. The Obel coefficient K may be assumed as 0.004 per meter. Calculate the stress in the cable at the remote end and at the 2 points where the arrangement of the cable changes. Assume the coefficient of friction between the cable and duct as 0.4. What is the percentage loss of prestress between the jacking end and anchored end? Okay. So in this problem you have a cable profile with some segment pattern. So total span of the beam is 12 meter. Out of 12 meter, the center 6 meter span is horizontal and the remaining 6 meter, 3 meter on either side is sloped with 0.075 radians. So you can observe in the figure, AB is the span of the beam of 12 meter. CD is the portion where the tendon or cable is provided in horizontal way, and AC and DB, it is straight portion with some slope, that is 3 meter on either side. Okay. So in this problem it is given end B is fixed. Okay. End B is fixed and from end A we are applying the tensile stress. From end A we are applying the tensile stress. So obviously there will be certain amount of prestress is going to lose from end A to end B. So in previous problems we had parabolic or circular profile cable, so there is a gradual change in the orientation of the tendons, but in this problem it is segmented. There is a sudden change in arrangement of the tendon. So the point where the profile of the tendon changes, there we need to find what is the prestress, and from A to B what is the total loss in prestress, what is the actual prestress we have at the B, that is anchored end, and what is the percentage of loss we need to find out. So for this problem we need to consider segment wise. First we need to calculate for AC, then CD, and then DB. First let us start with AC portion. So if you take AC portion, A is the point where you are applying the stress. So you need to find out what is the stress at C. At A you are having certain slope that is of 0.075, that is theta A, and at C it is horizontal, so slope will be 0. Theta A plus theta C, you will get alpha. X is the distance from A to C, that is 3 meter. From A to C we have distance 3 meter. Consider the loss of prestress formula, P naught into mu alpha plus Kx. Mu is given, K is given, alpha we have calculated, and X is 3. Substitute and simplify, we will get 43.68 Newton per mm square as the loss of prestress. This is not stress, this is loss. Then the stress what you are applying at the point A, that is 1040 Newton per mm square, minus the loss from A to C. If we do that, we will get what is the actual stress is at C, that is PC. So stress at C is 996.32. Next portion, CD, that is horizontal portion. So since it is horizontal, theta C and theta D both will be 0. So alpha will become 0. X is distance from C to D. It is 6 meter. And remember, here initial stress, you need to consider stress at C, not stress at A, because you are calculating from C to D. So you need to consider the stress at C as initial stress, that is P naught. Then substitute in the same equation, calculate the loss, that is 23.91 Newton per mm square you got. Then stress at C minus loss of stress from C to D, we will get what is the actual stress at D, that is 972.41 Newton per mm square. Next further we have portion DB. Here slope at D is 0 and slope at B we have 0.075 radians. Alpha we get. X is again from D to B we have 3 meter, that will be X value, and P naught initial stress will be stress what we have calculated at D, that is 972.41 will be P naught. Substitute, we will get the loss. Then stress at D minus loss of prestress from B to D, we will get stress at B. So stress at B is 931.57 Newton per mm square. Now what is the total difference applied stress and stress at B? That will give the total loss, that is applied stress at A is 1040 Newton per mm square and we remain at B with 931.57 Newton per mm square. So there is a difference between stresses. That difference is total loss. We will get 108.43 Newton per mm square. That is the loss from A to B. Then percentage loss of prestress by applied stress into 100. 10.42 is the total percentage of prestress lost. Let's move on to next problem. A concrete beam AB of span 12 meter is post tensioned by a cable which is concentric at supports A and B and has an eccentricity of 200 mm in the mid third span with a linear variation towards the support. If the cable is tensioned at jacking end A, what should be the jacking stress in the wires if the stress at B is to be 1000 Newton per mm square? Assume the coefficient of friction between the cable duct and concrete as 0.5 pi and the friction coefficient for wave effect as 0.0015 per meter. Okay. This problem is similar to previous one. Here few small changes it is given. Okay. One thing is the total span is 12 meter and middle third span, that is if you divide the total span into 3 segments, the middle segment is horizontal. So 12 meter means you will get 444 meters each segment. So middle 4 meter is horizontal and end 4 meters on either side is inclined. Here the slope is not given, he has given the eccentricity. So the eccentricity is from centroid to middle portion, that is horizontal portion is there, right? So for that we have 200 mm. So you need to find out the slope. So we will calculate it later. Then here one condition is given. end B is anchored, that is fixed, and end A you are applying the stress, that is jacking end. From end A you are stretching the tendon or applying the tensile force at end A. But what is the stress you are applying, it is not given, but you need to maintain the stress at B, that is given. If you want to maintain the stress at B of 1000 Newton per mm square, then what should be the stress you need to apply at end A, that you need to find out. That is the question. Similar to previous problem, you went from A to B, but in this problem you need to come from B to E, that is reverse way. Next, slope. You have span. If you consider from A to C, it is 4 meter, and eccentricity, the distance from centroidal axis to C, it is 200 mm. So by applying tan theta we will get slope. So slope at A is, so we need to go from B to A. So first we will consider portion BD. From B to D, slope at B is 0.05 radians we need to calculate, and at D it is 0. X, from B to D we have 4 meter distance. Now in previous stress problem we were considering the stress as initial stress and loss we would have calculated, but in this problem stress at distance x is given, at stress at 0 we need to find out. So stress at B we will consider as Px. So if we want to maintain stress of 1000 Newton per mm square at B, what should be the stress we need to apply at D, that we need to find out. So P0 it will be unknown, initial stress is unknown. For that we have another equation, Px equals P0 into 1 minus mu alpha minus Kx. Mu is given, K is given, X is 4 meter, alpha we have calculated. Substituting we will get PD. That is, if you maintain 1034 Newton per mm square at D, then you will get 1000 Newton per mm square at B. Next come to DC portion. Slope at D is 0, slope at C is 0, so alpha will become 0, X is 4 meter again. Px, now Px will be what is the stress you need to maintain at D, and what is the stress you need to apply at C, you have to calculate. So that is Px will be stress at D 1034.66 Newton per mm square. If you want to maintain that, what is the stress you need to apply at C, you need to find out. Here P0 become Pc. Substitute the values, we will get 1040.90 Newton per mm square. It means if you want to maintain 1034.66 Newton per mm square at D, you need to apply the stress of 1040.90 Newton per mm square at C. Next again C to A, reverse. C is 0, theta A, again it is same 0.05 radians, X is 4 meters again, alpha we have. Now here again Px, it is stress at C. If you want to maintain 10409 Newton per mm square at C, what should be the stress at A, you need to find out. So substitute the values, we will get 1076.98 Newton per mm square. So that is jacking stress. If you apply the 1076.98 Newton per mm square at A, you will remain with 1000 Newton per mm square at B. So applied force is 1000. Force you need to apply is 1076.98 Newton per mm square. Let's move to the next problem. A concrete beam AB of 20 meter span is post-tensioned by a cable carrying a stress of 1000 Newton per mm square at the jacking end A. The cable is parabolic between the supports A and B and is concentric at the supports with an eccentricity of 400 mm at the center of the span. The coefficient of friction between the duct and the cable is 0.35. The friction coefficient for wave effect is 0.15 for 100 meter. Calculate the stress allowing for losses due to friction and wave effect at the following points. First point is, assuming the jacking end as A, compute the effective stress at B. Then, if the cable is tensioned from both ends A and B, calculate the minimum stress after loss in the cable at its location. Yes. See, in this problem, we have parabolic profile with zero eccentricity at support and eccentricity of 400 mm at the midspan. You have two conditions. First condition is end B is fixed and you are applying the tensile stress from end A. In this case, what should be the stress at B you need to find out. At A you are applying, how much it is? 1000 Newton per mm square. So what will be stress at B? So slope, as usual, by considering parabolic equation, first derivative, that is tan theta is equal to first derivative of parabolic equation, we will get the theta A, slope of the tangent. Then theta A and theta B both will be same since eccentricity is same at both ends. Then alpha equals theta A plus theta B. Mu is given, K is given. Now effective stress at B. This will be done in two ways. One is by using only P naught into mu alpha plus Kx, you are going to get the loss. Then applied stress minus loss, you will get same answer. If you take it as Px, then by using this formula, you can directly get the stress. If it is asked to calculate the loss, then P naught into mu alpha plus Kx. Here stress is asking, so you can directly take this formula. So if you apply 1000 at A, you will remain with 914 at B. Second case, here it is important one. In first case, end B is fixed and end A is jacking it. That is, you are applying the stress from only one end, that is at A. But in second case, from both ends you are applying the stress. From A as well as at B, from both ends you are stretching the tendon with same magnitude of stress. In that case, what will be the location of minimum stress and what will be the stress? So obviously, if you stretch the tendon from both ends, at midspan, at center, there will be minimum stress. If the span of the beam is 20 meter, the minimum stress will be at 10 meter. Slope will be same again, but since you are calculating stress at midspan, the tangent will be horizontal, so the slope at midspan will be 0. Let us consider it as theta C, that is point C. If you observe the figure, you can understand. At C it is horizontal, so theta C will be 0 and remaining is same. Substitute the value, you will get the answer. So here we have calculated the loss first, then we calculated the stress at C. Both ways. Here you can directly consider Px is equal to P naught into 1 minus mu alpha minus Kx. So you will directly arrive with 957 Newton per mm square. Here first we have calculated loss and then by initial stress we deducted the loss. We will arrive with actual stress. Next problem. A concrete beam of rectangular section 100 mm wide and 300 mm deep is prestressed by 5 wires of 7 mm diameter located at an eccentricity of 50 mm. The initial stress in the wire being 1200 Newton per mm square. Estimate the loss of prestress in steel due to creep of concrete using the ultimate creep strain method and the creep coefficient method. Use the following data. Elastic modulus of steel 210 kN per mm square, elastic modulus of concrete 35 Newton per mm square, ultimate creep strain 41 into 10 power minus 6 per Newton per mm square, creep coefficient 1.6. So in this question, you need to find out the loss only because of creep of concrete. So you have two methods as I explained in theory part. One is creep coefficient method and another one is ultimate creep strain method. So first you observe the formulas. What is the data we require? If you take ultimate creep strain method, the formula has ultimate creep strain into Young's modulus of steel into sigma c, that is stress in concrete at the level of steel. If you take creep coefficient method, creep coefficient into modular ratio into sigma c, again stress in concrete at the level of steel. So here ultimate creep strain is given, Young's modulus of steel is given, creep coefficient is given, modular ratio it is ES by EC we can calculate. But this sigma c value we need to find out. So to calculate sigma c, we have the formula sigma c equals P by A plus M by I into Y. So P initial pre-stressing force, stress in steel into area of steel. So 5 wires of 7 mm diameter is given. We will get 230 kilonewton. Then area I E. Here in this case, centroid and the location of cable is same. So Y is equal to E only. Substitute the values. We will get sigma c as 10.2 Newton per mm square. Then substitute in these equations. By using ultimate creep strain method, we get 87.82 Newton per mm square, and by using creep coefficient method, we will get 97.92 Newton per mm square. Need not to be same values. These values will differ. For these formulas are available in IS 1343 code book. You can go through it. Next problem. A post-tensioned concrete beam of rectangular section 100 mm wide and 300 mm deep is stressed by a parabolic cable with zero eccentricity at supports and an eccentricity of 50 mm at the center of the span. The area of the cable is 200 mm square and initial stress in the cable is 1200 Newton per mm square. If the ultimate creep strain is 30 into 10 power minus 6 per Newton per mm square and modulus of elasticity of steel is 210 kilonewton per mm square, compute the loss of prestress in steel only due to creep of concrete. Okay, see in this problem, see the data given. So cross section is given, parabolic cable with zero eccentricity at support and eccentricity of 50 mm at midspan. So here it is parabolic profile. Then area of steel is given 200 mm square and initial stress in cable is 1200 Newton per mm square. So stress in steel into area you need to do. See, if ultimate creep strain is, so here it is given ultimate creep strain method. He is indirectly telling you need to do it with ultimate creep strain method. If he is given creep coefficient, then you need to go with creep coefficient method. So first stress in steel into area of steel, we will get pre-stressing force, then area, moment of inertia, eccentricity we have. Since it is parabolic profile, we need to take the average stress sigma c at support and sigma c at midspan. The average of both we need to calculate. So first it is sigma c at Support eccentricity is 0. Sigma C at midspan eccentricity is 50 mm. So both Y and E will be 50 mm. The average stress will be 9.78 Newton per mm square. So loss due to ultimate creeps in concrete by using ultimate creep strain method. The formula is ultimate creep strain into Young's modulus of steel into sigma C. So by substituting values we will arrive with 61.61 Newton per mm square is the loss of prestress due to creep of concrete by using ultimate creep strain method. Thank you.